Hello, everyone. Thanks for joining. This is going to be recorded, so if you're seeing this later, yeah, welcome to the competition. You're going to be reviewing my code today, which is Angstrom Core. So to give you first maybe an overview before we start diving into the code, and this is from debugging locally. Yeah, so before diving into the code, I want you to understand the overview of what the Angstrom protocol is, because the contracts are only a smaller piece of a larger protocol, and you're only reviewing the contracts, right? So there's certain things you'll need to black box, but also partially understand to be able to really get the protocol. And I've outlined these in the docs as well. But basically, Angstrom as a whole is a decentralized order book AMM protocol that it's basically like an exchange. It's like Binance, but trustless, basically. And the goal here is to mitigate some MEV for traders, as well as for Uniswap LPs. So in some ways, we're similar to CowSwap in the sense that off-chain users will send us their signed orders. We will collect and match them to each other in an order book, and we will also partially match them against the AMM where necessary. And then we'll build a bundle, what we like to call a bundle, which is just a big batch of different AMM swaps, of user trades, and we're going to submit those to the contract. And the contract that you're auditing here today is in charge for validating that batch and also for executing and settling it, right? So what it's not in charge of, for example, it's not in charge of ensuring that the price is fair, right? That's part of the off-chain mechanism that's going to be audited later, but we have if you're interested, we have a set of off-chain nodes. They run their own consensus algorithm. They're going to be secured by EigenLayer, yada, yada. That's all still in development. Right now, you're just auditing the batch settlement contract here, or what I like to call Angstrom Core, right? The core part of the contracts. So there's certain things that we do want the contract to check. Like, for example, we want the contract to check that, hey, you can't just arbitrarily take people's money. You know, it has to be based on orders they actually signed, that you can't like resubmit orders, that you always have to respect their limit prices, that within the same batch, everybody has to get the same price, even though we don't know how fair or not fair that price is. I mean, not including the fee. And basically the contract, from a design perspective, the contract wants to validate as few things as possible because of gas, right? Because we have this off-chain consensus algorithm, we can offload a lot of the trust assumptions to that, but also they have a limited amount of stake, right? So if you allow these nodes to just arbitrarily draw funds from the contract, that would likely far exceed the potential stake, right? So there has to be a balance of like what we check on chain to reduce the amount that a malicious node can potentially steal on their own, and what is checked off chain, because checking it on chain would be expensive and wouldn't reduce the potential damage by that much. So let's dive into the actual contract and like how it's built up. So the contract is a Uniswap v4 hook. That means we can build on top of Uniswap v4, and we'll have our own liquidity pools within v4 that have special rules. So the first rule that our Uniswap pools have is that nobody is allowed to trade with them except for us. So what that means is that unless you submit a batch here, you're never going to be able to swap with our pools. Like, thanks to the before swap hook, it should revert. We don't actually implement the before swap hook. So when you call our contract with it, it'll just revert, right? So that's kind of the first piece. And then the entry point to everything in the contract is basically this execute and unlock callback methods, right? So the way Uniswap v4 works is that when you want to do actions against Uniswap, like swapping, adding liquidity, etc., you need to be in a call context that it controls so that it can do things like checking the invariance and whatever. So execute, as you'll see, calls into Uniswap v4, unlock, and then Uniswap v4 will call back to our unlock callback to actually start executing our bundle. And the data here is the payload. So as you see, it's just bytes. You don't see any types. And this is because we also use a custom call data in encoding format. And if you would like to see it, it's in the docs. So under docs, PADE encoding format is the actual format. and then payload types is the types that go into the contract. So you can see them there. And then we start the process of actually processing the batch step by step. So the first part is we decode some tables that we will use throughout the transaction. So this is the list of assets and the list of pairs. We read and validate them, right? So we want to validate that the assets are unique. We do this by just checking that the list is sorted. We want to validate that the pairs of assets are unique, because we will, together with the pairs, we also have the actual price for the pair and the fee for the pair, right? So we want to ensure those are supplied in a unique manner by the node. So we're checking that here. So this is like validation and decoding of the asset and pair list. And then we go into like actual accounting. So for example, we have the first part of the actual execution of the batch, which is take assets. So if we go to the settlement module, which is where this is implemented, take assets goes through and it takes tokens from Uniswap. So this is necessary for two reasons. Either one, it's to actually get the output of a swap. So if we do a swap against the AMM later, we can get the amount. Sorry if you hear some noise, that's the washing machine in the background. But yeah, we need to take money from Uniswap, because basically the way Uniswap works is that within a call, you can pay the input, take the output in whatever order you want, because basically it's just added against each other, right? If we take first and then swap, well, we'll owe some money, and then when we swap, it'll cancel out the debt, right? So we can do it in whatever order we want. So take is both for settling the AMM swap, but it's also for potentially flash borrowing, right? If our contract doesn't have enough tokens to settle orders in between, even though the batch as a whole has enough tokens, then we need to borrow some, and then we pay them back at the end, right? So this is what take does. Take goes through, it takes tokens from Uniswap, and then we, similar to Uniswap, we have like a delta tracker that ensures that by the end of the batch, that all things add up, right? So that's the first part. Then the next part is what we call update pools. So what update pool does is it executes AMM swaps, and also it distributes rewards to LPs, because our AMM pools, they will have, on the from Uniswap's perspective, they will have no fee. So we have our own mechanism for computing and distributing fees, because if you look at Uniswap, it only has the ability to reward the current tick, but potentially, like, let's say we swap over like 3 tick ranges, we may want to reward the LPs in 3 different ranges. So how exactly this is distributed and how like the set of fees is split across different ticks, that is determined off-chain. What the on-chain contract does is ensures that it's actually accounted properly and split across. So if we look at the update pools, we loop through, and then what we do is we loop through, and then we have an update pool. So we have a bunch of stuff related to fetching the pair, decoding, whatever. And then we actually execute a swap against Uniswap, like the actual AMM, because as the hook, we're the only ones allowed to do that. The accounting for the rewards. One kind of counterintuitive thing is that we don't actually, on our side, we don't need to account the swap amount, because Uniswap accounts that, and our way of talking to Uniswap does the accounting. So you'll see here that the accounting only accounts for the rewards distributed and not the Uniswap swap amounts. So that's the next part. We so-called update the pools. So we execute a swap if we have an amount, and then we also distribute rewards. Here, we don't enforce that updates are unique, right? Because a node has the ability to swap against the pool anyway. So if it does it in one swap or multiple swaps is kind of irrelevant. Obviously, it's more efficient to do it in one. So that's what we expect the node to do. But it's not an issue that it can do multiple. And in some edge cases, we actually need to do multiple updates for a single pool, because we may need to reward on both sides of the current tick. But you'll see what I mean once you start diving into the contracts. So that's one part. Then after we've updated the pool, so after we've executed the AMM swaps and distributed rewards, it's time to actually process settle and execute orders. So we have two categories of orders. One that we like to call top of block orders, and one that we like to call user orders. So the reason they're called top of block is because top of block orders are special orders to be submitted by searchers or like sophisticated actors that want to arbitrage the AMM pool. So these are not normal user orders where they say, hey, we have a certain limit, we just want to swap tokens, whatever. They say, hey, the AMM price on chain of the Angstrom pool is at a certain price, Binance is at another, so I'd like to buy from the pool and sell on Binance to make a profit, right? And this is kind of also how we want to protect LPs from MEV, because what we do off-chain, is we have different orders compete in an auction to basically say who will get to do this swap, right? Before the pool is updated to the new price via this arbitrage, who will get to do it, right? Because there's some free profit involved. And ideally, we want the LPs to capture most of that profit. So we run an auction to see who will actually be the winner. And then the winners get submitted by the node, and these are the TOB orders. So unlike other orders, they just specify the input and output amount, and then disconnected, we do the swap, right? So next step is cycling through and validating those. So we validate those, we decode the different fields step by step, and then we do different calculations related to the input amount, output amount, and then we validate signatures, etc., blah blah blah, before actually transferring the amount. And then these functions, as you'll notice, settle order in, order out. Again, they do some accounting. They do a transfer or use internal balances based on what the order has chosen, and then it's done. Then we come to user orders. User orders are very similar, except that instead of having an exact in, exact out, they have either input or output, and then they specify like a limit price, and that limit price is checked on chain. And all user orders against the same pair are guaranteed to have the same price. Note that, for example, if we have a pair from A to B and a pair from B to C, and people are swapping also from A to C, that it's not guaranteed that the conversion rate from A to C is the same as A to B times B to C, right? So actually, I should add that to the list of known issues, but that's a thing that is to be guaranteed off-chain, but we just check that each like connection has the same price, all right? So yeah, we go through, we decode fields, we do different checks, we check the signature, and then it's done. And that's pretty much the overview over the contract's functionality, right? So now we can dive into details about individual pieces and how they work in some more detail, and I can just like skim over, give some thoughts about how and why we did things. But so far, any questions? If you have any questions, feel free to write them into the chat. If you're just joining now, then don't worry, this is going to be this is recorded, so and will be uploaded later in full. But yeah, if you have any questions, feel free to post them now in the chat. All right, since there are no questions, I'll continue with the deep dive. So maybe the accounting system, right? So the accounting system within batch that checks that things add up is the so-called delta tracker. So it allows negative and positive like net amounts in the contract, but by the end, it checks that these are all zero. Actually, this is a step that I forgot to show, is that after we validate the user orders, we check that all the amounts are settled up, right? So we go through the whole list of assets in the batch. We check that the final delta is zero, and then if we need to pay something back to Uniswap, like the settle amount, then we do that. And then there's also this special thing in our contract is that the way we collect fees in the contract to save gas is quite special. So the way we do it is we don't directly account it. What we do is we put together all the fee collection into a big list, we hash it, and then we emit an event. So this is what's happening here. This is the so-called fee summary. Because while this is not part of the audit, we're still developing this. But what we're going to do later is we're going to use a ZK VM, namely most likely SP1 or RIS0 or whatever, to basically go back through history, check these fee summary events, and then compute the total and pull the amount out. And the reason this is cheaper is because we don't have to do a storage update every single time we post a batch. Instead, we can just have these events, and later trustlessly another piece of the system will check and pull the funds. And actually, if you look at the module of the contract that manages all the authorization, you'll see that there's this magic controller address that will be a contract. It's not part of the audit because we haven't written it yet, but there will be a contract that controls all the special abilities of our contract, like adding and removing nodes. And it has this function called pull fee that is able to pull an arbitrary amount. So obviously, if controller is malicious, it can do whatever, but that's obviously one of the assumptions. Known issue. Don't submit issues about this, that it can do this because we expect controller to be a trustless smart contract. But it's not written yet, so it's not in scope. This could be what else. The custom encoding format. You'll see it all over. Like, for example, when we validate user orders, you'll see that basically the pattern of how this decoder works is that it's basically just ABI encode packed. And then there's a few special ways of handling like lists and variable length data. But basically, the encoding is just ABI encode packed on everything. So when we decode is we have this like reader object. And what we do is we decode like one field at a time. So for example, if the next field to decode is like a U16, then we have read U16. That'll advance the reader by 2 bytes, and it'll give us out a U16 value. Or if we want to read a UN256, then we have, again, a read U256 method that'll advance the reader by 32 bytes and read out the value. And this is kind of the general pattern that is done all over in the contract to do this. Another thing you'll notice in the contract is we have this pattern of having different buffer structs or buffer custom types. So the idea behind this is that if you think about how Solidity handles memory allocation in the background, it will always allocate a new chunk of memory for a new struct or a new call, right? And this can add up, especially if you have a larger batch, it can add up quite quickly. So what we do in the contract is we have one struct that is the buffer, that is our one-time memory allocation. So when we do this, we tell Solidity one time, hey, we're going to have a struct, and Solidity is going to give it some memory. And then this struct gets reused for every loop iteration. So no matter how many orders we process, for those fields, they're going to use the same area of memory, right? Because we reinitialize the buffer, we set different fields, and then we have other buffers, like we have buffer for hook, because in our system, orders can have their own hooks if they want to do something special. So we have our own buffer for that. And this way we minimize memory usage. Like we also do this in pool updates. If you'll notice, we have this special buffer-like struct called swap call, which basically stores the ABI encoded parameters for the call to for the swap against Uniswap. Like this, we can have the same area of memory reused between iterations. And we use this pattern all over. You'll notice this pattern. Then one big part of the contract that also during testing and during our previous audit has led to issues, and where I think you're still most likely to find issues is the pool reward logic. Because it deals here with accumulators, similar to Uniswap, and there's always weird edge cases with ticks and boundaries and swapping across them that leads to issues. So I recommend this is where you like dive in and look over things, because I think this is still where you're, even though I think this time it's actually like good, obviously I think this is still the area where you're most likely to find an issue in the contracts. This is reward logic. And I wrote some nice docs and diagrams explaining how different pieces of this work. Yeah. Then what else can we dive into? Well, there's a lot of pieces. I'm not sure in how much detail I should dive in here, or unless I can just keep going for, and I can easily keep going for another like 40 minutes about different details of the contract. For instance, the way we let me go. I think this is a good thing to look into. So the way we have a list of pairs that are active or not active in the contract, but instead of using storage, we use a so-called SSStore2 pattern. Yeah, I see. Mostly ammunition for the gun. Yeah, I think this is also a good area to look into, because we have some bugs here, and it uses a lot of assembly and some novel patterns. So I think this is also a good area to look into. But essentially, we use the SSStore2 pattern here to store the list of active pairs in the contract. And basically what this means is that instead of storing it as contract storage, anytime you update this list of active pairs, we deploy a new contract, and the bytecode of that contract holds the information, which has some gas benefits in terms of reading that information. And then we have this thing here called pool config store that manages that. So as you can see here, like if you in the method set into new, which adds a new pair, we go through, we potentially override it, and then we deploy a new contract here. Right? We deploy a new contract, and that's our new store that actually stores this. That actually stores the entries. So this is quite a novel pattern. The auditors from Spearbit previously found a I don't think they didn't find a bug here, but they did find a common issue. But yeah, this is potentially an area you can look into. Also, in general, a lot of assembly is used. So assembly has a lot of footguns, like if you assume that small types are truncated when maybe they're not, then that can lead to bugs. So anytime there's assembly, always double check. Good to look into that stuff. Then another area that's worth looking into is the accounting and management of orders. So to ensure that the order semantics are like actually correct. So for example, that an exact in order really means that this will be the exact amount consumed by the order. And yeah, checking that the amounts are actually always accounted for, that there's no weird things going on with like the buffer, like if that certain values are not overwritten or stuff like that. I think that's also good to look into. Then what else? Um, what else is a good target for the auditing? I mean, that goes over most of the stuff. Then, oh, also one thing I wanted to quickly explain is we have this very unique pattern for order invalidation. So we have two types of user orders. We have so-called standing orders and flash orders. So standing orders are very classic orders, right? So there's a timestamp deadline, and there's a nonce associated with it, and then we check and invalidate that nonce if it's been used to avoid reuse of orders. But then the flash orders are quite interesting, because flash orders are made unique by their block number. So basically, if you imagine that you're a trader who actually is using like a bot or something automated and you're trading with this, then you don't really need to worry about nonces or deadlines because usually you either want your order filled that block or not at all. So to accommodate this use case, because it actually saves a ton of gas to have this, we use transient storage to keep track of within a transaction what orders were already executed or not based on their order hash and signer. And then we have a unique reentrancy lock at the beginning of our contract. Uh, oh, at the beginning of our contract here, the node bundle lock that actually checks that that the contract is only ever executed once per block. So it's like a reentrancy lock, but beyond reentrancy, it not only checks that per call you only call it once, but it also checks that per block you can only call it once. So I think that's pretty unique thing that deserves being looked into because yeah, who knows, maybe there's some issue there that I overlooked. And then yeah, it leads to some pretty huge gas savings to be able to do that. Because instead of like having to update a full storage slot to invalidate an order, it's just transient storage, which is much cheaper. And you'll see that for top of lock orders are all flash. And then we have, the different variants of the user orders. So I think that's something worth looking into. Yeah. Otherwise, I think that's pretty much it. I'll be peeking into the Discord every now and again, and you can use I think they're called the Cantina pings or whatever to ask questions. And yeah, I'll be browsing over the Discord. If you have like general questions, please always yeah, I will try to avoid doing the thing where I accept DMs, especially because Cantina has this ping system. But if yeah, if you really need to, then feel free to ask about DMing. But yeah, try to use the Cantina ping system first, or just post your question publicly if it's not sensitive. Um, and then yeah, happy hunting. Starts later today, I think in like 6.5 hours. So yeah, excited to have you look over and help us secure our code. And yeah, have a good one. Bye bye, everyone.